Thank you and good morning. Thank you very much for the invitation to talk to you this morning too. I will be talking this morning about work focused on research evidence for effective mathematics teaching and learning. And I just wanted to start by giving you a little bit of background for what I'll be drawing upon. So in 2023, I think it was, I was lucky enough to be awarded a visiting professorship to work at Loughborough University in the UK over a period of 6 months and work with colleagues there. And Loughborough University has the largest funded centre in the UK, which is focused on cognitive science and mathematics education. So I was very privileged to work with a number of colleagues there and learn about different aspects of cognitive science and how that relates to mathematics education. And one of my kind of concerns I've noticed in Aotearoa New Zealand over the past few years is the presentation of evidence for effective mathematics teaching, which claims to be based on the science of learning, which underneath the science of learning is cognitive science. But instead we've been, I think, kind of sold a very narrow view of what cognitive science is and the findings that we can take back to think about our mathematics teaching and learning. So I guess to me what was stark was when I saw what my colleagues are looking at and researching in terms of mathematics teaching and learning related to cognitive science, and what we're being told cognitive science says here through the science of learning kind of rhetoric are two quite different things. So today what I'll be presenting on is the findings from cognitive science, which I'll be largely drawing on a quite influential report, which was from the Education Endowment Fund, which is one of the biggest syntheses that has been undertaken of evidence for the classroom in terms of cognitive science. And then I'll also be connecting to research studies which are from mathematics education, which have been influential, looking at what is effective for students' achievement and students' mathematical achievement and what is effective for well-being, I guess, or positive emotions towards mathematics. So I'll be first presenting the evidence from the kind of cognitive science side, then the mathematics education side, and then conclude by trying to draw these together. So just to kind of ground what I'll be talking about today, I think it's really important for us as teachers and educators and researchers to think about what the purpose of mathematics education is. So when I'm thinking about the purpose of mathematics education, I start thinking about these future-focused competencies, because mathematics education and all education really is about focusing both on the knowledge that we develop in the classroom, but also the competencies that children walk away with. So I've just started with a little bit of a mind map of the types of future-focused competencies that we should be thinking about when we're working in our classroom. And this is just to ground the rest of the talk. So we've got things like critical thinking, which are really important, deep learning, integrative problem solving, communication, creativity, collaboration and teamwork, self-management, and global citizenship. And I think what you will be able to see both through threads of cognitive science in terms of mathematics education and the mathematics education research that I'll be drawing upon is that all of them are connected to these future-focused competencies. So the big picture is these are the kinds of outcomes that we want children to walk away from our classrooms and schools with. So currently, I think in New Zealand, we've entered a phase which a number of other countries have had at different times, which the phase that's been bandied around starting in the USA, where this kind of began, was this idea about kind of a maths war. So arguments about how to teach mathematics and what is the best way and what gets the best outcomes. And I think it's very unhelpful to engage with this kind of dichotomy, which is currently the narrative that we have going on here and that's happened in the USA. So some of these kind of positioning and dichotomy ways of thinking about things are this idea to begin with of the role of the teacher. So we've got two positions here, either teachers as technicians, okay, and if we're thinking about this idea of teachers as technicians, a technician just follows a predetermined script A technician is given specific tasks and just focuses on producing these in individual circumstances. Okay, and I kind of connect this to ideas about using textbook scripts and things like that. So our job as teachers, when we're given predetermined textbooks and scripts and things like that, is that we're just delivering the mathematics curriculum through these outside resources. In contrast, if we're thinking about teachers as professionals, then we can think about drawing on the kind of complex noticing that we use in the classroom, using our judgment to make decisions, and using this knowledge base that we have of individual students and being a reflective practitioner. So if we're thinking about teachers in a professional role, those are the kind of attributes that we're thinking about. And this kind of connects into what I'll be talking about today in terms of thinking about how do we want to be viewed as teachers and as professionals. So the second aspect that I think we can think about too is so then connecting through this idea about our role as a teacher, then it's thinking about what is our role in the classroom. So is our role in the classroom to teach procedures, procedural fluency, or is our role in the classroom to teach for understanding, conceptual understanding? Again, I'd argue in this kind of framing that actually saying either or, this dichotomy, is unhelpful. Instead, we need to be thinking about both at the same time. So as teachers, we want to develop procedural fluency. And just to give you a little definition of it. Okay, so procedural fluency is supporting students to be able to accurately, efficiently, and flexibly apply mathematical procedures, transfer them to different problems, and choose the most appropriate strategy. Okay, and I like to use an analogy of a recipe when we're thinking about procedural knowledge or procedural fluency. So procedural knowledge, for example, would be when you're able to follow a recipe correctly. And that could be, if you put that into the context of mathematics, that could be that you can follow an algorithm, for example, to find an answer, or even simple things like being able to remember the names of a shape. Okay, so these are things that we want children to have, but standing by itself, it's not enough. So we also want children to have conceptual understanding. And conceptual understanding, as you can probably see from the much longer explanation, is much less clearly defined. And it can be difficult to recognise, but conceptual understanding is really referring to this kind of integrated and functional grasp of mathematical ideas. And students have got conceptual understanding no more than isolated facts and methods. They can understand why a mathematics idea is important and the kinds of contexts in which it's useful. And so they organise all of their knowledge into this whole, which helps them to learn new ideas by connecting to the ideas they already know. If I'm going to go back to my cooking analogy, so sometimes I'd say, well, not sometimes, I think for most people, understanding how a recipe works and then how you can innovate on that recipe, that would be your kind of real world analogy to what conceptual understanding is. So if we take that into a mathematics classroom, if you're talking about the algorithm example I said before, it might be that when the student's using the algorithm, they understand that the one above represents a 10 or 100 rather than just the digit 1. Okay. So when we're teaching in the classroom, we want to be developing both procedural fluency and conceptual understanding at the same time. So this kind of dichotomy of it's either procedural fluency or procedural knowledge or conceptual understanding, again, is unhelpful. We need children to be developing both while we're teaching. And the final piece that I wanted to draw on in this kind of positioning is this idea about teaching as direct or explicit instruction, or teaching as inquiry and problem solving. And again, I think having this dichotomy of either or is unhelpful. I'm probably telling you something you already know. I think when we're talking about teaching, there's different times and different moments when we're teaching with explicit instruction, and at different times we're teaching with problem solving and inquiry. So it isn't about either or, it's about when do you use this type of teaching. It might be when you're introducing a new topic, you're using more direct or explicit instruction. And then at other times when you know that the children have the requisite knowledge that's needed, you're able to use problem solving and inquiry as well. Okay, but the way I like to think about this, or this kind of diagram, is just thinking about this kind of idea of passive learning versus supported or explicit teaching. So if we're thinking about a kind of passive delivery approach, we are assuming either, well, there's two ways that we can think about this. And in the diagram here, I've got, there's sometimes can be an assumption that students possess the requisite background. Also, it can be the assumption that they don't possess it. So we start trying to teach them what they already know. If we're thinking about supported explicit teaching, we begin our lessons by prompting students to think about what they know before they start solving something. We think about, if we're thinking about a passive delivery with errors, we just simply provide children with the correct answer when the students fail. If we're thinking about explicit teaching in this framing, we're actually asking children to work through errors and misunderstanding with our support, or targeted support, so it might be support from peers. Similarly, if we're thinking about the kind of passive delivery, we accept children's final correct answer as proof of understanding, whereas if we're thinking about supported explicit teaching, we're thinking about requiring elaboration or explanation of why solutions work. Okay, I can think back to my own teaching, and just to give you an example of this, when I was teaching primary school and in my early years of teaching, I was teaching a unit on angles for the first time, and I had made a great lesson plan where I was planning to teach all the children that 360 was a full turn and 90-degree angle and 180 was a half turn. And so I'd planned out all of these activities where I was basically going to tell the children or kind of use direct instruction or explicit teaching. And instead I began the lesson and with all of this all planned out, and I began the lesson by instead doing this first prompt and asking the children, what do you know about angles? And all of the children then started putting the angles into their real life conceptions and came back in this group discussion that 360 was a full turn because it was basically, you know, when you're riding a bike and you're, or in a car and it does a 360 turn. And so they already knew all of this. So I think that's a good example of where we need to actually think about what do the children know, because I could have taught that lesson and none of those children would have walked away with any new learning from what I was going to tell them because they already knew that. And instead, by asking them, then I had to think on my feet and actually change the lesson and start thinking about how I could further develop their understanding of angles. Okay, so the role of explicit teaching then, if we're thinking about the context of developing procedural fluency and conceptual understanding, the role of explicit teaching in this context is about activating prior knowledge to begin with. It's about asking children to give explanatory elaborations. It's also about asking children to reflect, okay? And this is, I saw one of the sessions later today is on metacognition, and there's a lot of evidence to show the importance of metacognition in our classrooms. And reflective practice is a really good example of this. So we want children to reflect on both the learning outcomes and the learning process that they're using. But we're also needing to use explicit teaching. So as teachers, we need to use explicit teaching to bridge multiple representations. We want children to connect between abstract numbers, drawings, concrete materials. We also need to use explicit teaching to help children to connect across solving strategies. So we want them to see the connections between different mathematical solutions and different ideas. Okay, and in the last part, I also think it's very important for us to be thinking about explicit teaching in terms of errors, okay, and helping children work through misunderstandings and errors with either direct teacher guidance or support from their peers. Okay. So this next part of the session is moving forward, thinking about how we can connect to cognitive science approaches in the mathematics classroom. And like I said, I've drawn these findings from the Education Endowment Foundation Perry report. Perry was the lead author on this report, and you can look it up yourself. It's a very helpful document. Basically, the researchers who were involved in this have undertaken a very high-level synthesis of what is evidence for cognitive science approaches in education I've taken this and turned it into mathematics classrooms and mathematics education. They were actually looking at general education, and it's the largest synthesis of cognitive science approaches that's been undertaken. They've looked very carefully across all of the studies that they could find, and they, in the report, which I haven't gone too deeply in this, but in the report they also give a ranking of the robustness of each of the findings. But one of the things that I think is really important to note, and they do note this in their report, is that when we're talking about cognitive science, this is actually a different field than educational research. So if we're looking at cognitive science, most of this work has been undertaken in laboratories in very controlled settings. And these are tightly controlled settings. They have single variables. Often it's researcher-led rather than teachers leading it, and it's artificial environments, okay? When we're talking about mathematics education research, this is a type of applied science. So instead we're looking at what happens in a classroom. It's a messy reality. It has lots of variable conditions which are influenced by the pupils or students' prior knowledge, their emotions, the teacher, and social dynamics in the classroom. So one of the kind of insights from this report is that they say a lot of the work that's being undertaken in cognitive science using the scientific approach, that it hasn't largely been tested in the classroom. So there's a gap between what we can say definitively from cognitive science and what we can say works in the classroom. And they talk about, so in this, they're talking about applied classroom evidence. And they're saying that because the studies which have just been undertaken in a lab, that we can't definitively say that it will work the same way in a classroom when you've got a whole lot of variables going on. But out of what they've done, they've basically identified a number of principles that could be helpful in the classroom with kind of variable levels of evidence for it. And that's what I'll just be talking about now. So the first principle that they identify is this idea of spaced learning. And I don't think this is very unusual for any of us who teach mathematics. Basically, spaced learning is this idea about teaching topics across days or across lessons, okay? And there's basically what they've found is that there's small positive impact in terms of having spaced learning. So they talk about massed practice. Massed practice is basically doing a whole lot of study. I suppose it would be the equivalent of cramming for a test, where you do a whole lot of study before something and you get high immediate performance, but over the long term, you get quite a rapid long-term decay. Okay, so it means basically that you might study very hard to memorize something. You can, within a short period afterwards, perform well on what you've memorized, but then a month or two later, you're not going to remember that. So what does this mean for our classroom? Well, it's really about returning to the idea or topics over time, using warm-up activities or independent practice tasks over time, which return to the previous learning and to concepts which have been taught previously. So this can be across days. It may be that you've taught something in term one and you're returning to it as a warm-up or independent activity later, but the idea is that you are teaching things across days and using this kind of spiral curriculum. One of the key barriers to this, however, is this kind of like pressure that we've got based from curriculum to cover lots of learning material within a limited time frame. So in fact, if you're looking at the findings of cognitive science, they're saying really that we should be teaching less and returning to those topics multiple times rather than having a curriculum which has got a lot of content in it and that we don't have the time to return to. Okay, the second approach that they say has relevance for in the classroom, and this actually in fact has a lot of evidence for it. So spaced learning, they said, has some evidence for it, but not as much as interleaving. In terms of mathematics and science classrooms, interleaving has a lot of robust evidence for this, okay? And the idea of interleaving is using sequences of similar related tasks or problems. And the reason this is important is it can position learners to discern differences and think about the correct problem-solving method. So I've just got two examples here. One is if you were teaching fractions and using blocked practice. Okay, so where blocked practice will give students a series of problems which are all on the same concept. So for example, here in the green, you can see that this is all a whole series of problems where students are being asked to add two fractions together. More effective is using interleaved practice. So in interleaved practice, you may give students a similar related task. So in this case, we've got an example of where you give students a addition of fractions and then a multiplication of fractions. And then you go back to addition of fractions and then back to multiplication of fractions again. Okay. So if we're thinking about how this can impact in our classroom, we can be thinking about developing series or sequences of tasks which have slight differences in them. Okay, I think this is something quite often we've done as teachers as well, but it's doing it in a very purposeful way. And this one has quite robust evidence for it being effective in terms of mathematics learning. Okay, retrieval practices is the next one, which again has been undertaken actually quite across education in different areas as well. And I pull this up particularly because I think often retrieval practice has been thought of as being really about tests or quizzes. But in fact, when we're looking at what the report says, they're talking about retrieval practice as a low stakes classroom strategy. Okay, so it can be quizzes, it can be tests and things like that, but they also talk about things like asking children to begin by writing down or discussing, listing everything they know about a topic. Okay, so at the beginning of the lesson, for example, you might ask children to begin by listing everything they know about fractions. It can also be things like true and false. So using true and false statements, we are asking children to look at a whole lot of true and false statements and make decisions on whether they're true or false. Things like flashcards, another aspect that they pull out. So for example, you know, if you want children to be learning multiplication facts with younger years, using flashcards and things like that is really helpful. Making diagrams of what you know, which is what's represented in the purple there, and using kind of short types of problem solving as well. Okay, one of the key things they say that's important about retrieval practice is that it is really important to know that if students cannot retrieve the information successfully, that doesn't increase the learning, for example. Okay, so we need to be, this is really about practicing what children already know as opposed to introducing new material. Okay. We've had a lot of this kind of talk about cognitive load and cognitive load theory. So I think it's interesting for us to think about this idea of managing cognitive load and how do you manage cognitive load in a mathematics classroom. So if we're looking at the research evidence for it, the first example, which I think most people will be familiar with because we've had quite a kind of lot of talk about this idea of worked examples and different things. And I think that's something that quite often teachers use anyway. Okay, but I think the part which I find quite interesting is often when we've been presented with this idea of worked examples, it's always in the very first way, where in actual fact, there's lots of research talking about different types of worked examples which are effective. So your kind of common one, which is the one that teachers are often presented with, is that you use worked examples as simply giving a step-by-step structure and showing children how to do something. Okay, but in fact, the research evidence is that we can use worked examples, we can use a step-by-step structure, but there's also other types of worked examples. So you may use an incomplete worked example. Okay, and just to give you an example of what is meant by that, in some of the classrooms I've worked in, for example, we would use a introducing children to area measurement using squares, and we may give children a problem which involves tiling a space, a floor or something like that. And we'll give children a problem where it's got some of the squares filled in, but then they have to work out the missing squares from that. And that's a good example of an incomplete worked example. Okay, so it's giving the children the structure of how you find area using squares, but we haven't given it to them step by step. Instead, we've given this incomplete worked example, which the children then work together to work out what's missing. Okay. Other examples can be things like side-by-side incorrect worked examples. So you may give children, again, this is kind of problem structures that, I think are helpful to use in the classroom. So you may give them two examples of, for example, sorting out decimals or, ordering decimals from smallest to largest. And you may give them one which is incorrect with the student explanation underneath it, and another which is correct with the student explanation, and ask them to look at those and compare them and think about which is correct and which is incorrect and why. Okay, so that's kind of another way of using worked examples. And the final one is that you might give children side-by-side worked examples for comparison. So, for example, you might give children a problem which is adding two fractions together, and then you might, but fractions with different denominators. And then you may show the children two examples, one where somebody has used a common denominator approach to add the fractions together, and another where somebody's used decimals, and then ask the children to look at that as an example. Okay. Now, what's also interesting in this managing cognitive load, because I think it's something that's been missing from a lot of our understanding about managing cognitive load, is in the research evidence, they talk about collaborative group work as another way in which we can develop, in another way in which we can support children to manage cognitive load. Okay, so in this case, we're talking about collaborative group work because peer support can provide scaffolding for understanding in mathematics. Okay, and then your final part of managing cognitive load is thinking about scaffolding through things such as teacher prompts. So thinking about what prompts we're going to use to help children access the mathematical learning. Thinking about tools, so that's physical material or representations, and thinking about things like templates, for example, to provide a scaffold for children. Okay, I've just got a couple more here. So the next one that is identified in the Perry report is this idea about working with schemas. Okay, so in the report, they identify 3 key strategies for developing complex mental schemas. Okay, and if we're developing a mental schema that requires students to be able to organise and elaborate on their ideas. Okay, so the first one that they identify as effective is this idea about problem-based learning. So in this case, actually, sorry, I just wanted to go back to one point before I move on to this because it relates. Going back to the worked examples, sorry, and I'll just flip back to the slide. Okay, one of the key points with worked examples, because this connects to the next slide I'll be talking about, is that they do identify in cognitive science research that there's an issue with worked examples, which is called expert reversal effect, and that's the issue is using worked examples benefit learners when the context is unfamiliar, but in fact it becomes a harmful practice to be using as students become more familiar with the problem. So basically what cognitive research says is that if we know children are unfamiliar and this is new learning for them, it's helpful to use worked examples. But once children develop the expertise and understanding, in fact, it's the opposite. It becomes harmful for students to be given worked examples. So for that reason, as teachers, it's really important for us to be paying close attention to the students' learning and really having an understanding of what they know and what they don't know. And then connected to that, sorry, is this idea about working with schemas. Because once we're confident that the children have understanding of ideas, then a very helpful strategy to be using is problem-based learning. Okay, and this is where we're asking children to learn through the struggle of applying their existing knowledge to a challenging task. Two of the other strategies which are really helpful in terms of developing mental schemas are comparisons and analogies. Okay, and so you can kind of see how these approaches connect together. If we're talking about going back to the worked examples and we're giving students worked examples where we're asking them to compare different strategies, this then connects to working with schemas because we through those kind of worked examples and we're asking children to compare them, we can get children to add depth to their concepts. We can also use comparisons and analogies to address common misconceptions. Okay, then the final part of working with schemas is this idea about elaboration and questioning. So as teachers, we should be questioning to students and asking them to elaborate on their thinking. So questioning concepts strengthens, develops, and facilitates the transfer of learning. So we need to be asking children to come up with mathematical explanations. We need to be asking children to justify their reasoning and give explanations as to why it works and how. Okay, last two principles from cognitive science. This cognitive theory of multimedia learning. Quite interesting. There's a lot of colleagues of mine at Loughborough University who are working on this. But it's the idea about multimedia and when is that helpful and when is it not helpful. Okay, so for example, the cognitive theory of multimedia learning argues that using visual representations or illustrations can be helpful. And what this means is that learners are being presented with or creating images or pictures that represent the content being learned. It's helpful when the images are informational rather than decorative. Okay, so it's actually a really important point, especially when we're using outsourced resources. If we have pictures of, you know how quite often you have like the comic kind of pictures and textbooks and things like that. In fact, that's detrimental for students' learning. Images that are informational are images which would help you solve the task, for example. So an informational image might be an image of a fraction, for example. But an image of a bird or something like that, that in fact is unhelpful. Diagrams are another part of multimedia learning, which can be really important for students. So diagrams which represent relevant concepts and show how they're organised or structured. So this takes your images, your visual representations or illustrations from the above point, and then that can be formed into a diagram which represents the concept, but also shows how that concept is structured. Okay, and the last part of multimedia learning, which I think we probably would be all familiar with in terms of mathematics classrooms, is this idea about spatial visualization or simulation approaches. So these are things like imaging a number line or a tens frame to visualize how a calculation takes place. And in mathematics, again, there's quite a lot of robust evidence to show that these spatial visualization and simulation approaches are really helpful as scaffolds for problem solving. Okay, and the very last part that the review identifies is this idea of embodied learning and physical factors. Okay, so what does this mean? It's using gestures, for example, in mathematics is really helpful. So a teacher using gestures, for example, you might be doing work across equations and asking children to solve equations, and you're using representational hand movements to show the balance across an equation. Okay, there's also quite a lot of research about tracing, for example. So teaching children about shapes to begin with, asking them to trace with their fingers around the shapes while you're talking about the properties and attributes of the shape has been shown to be positively impacted, has been shown to positively impact children's learning. That's a really important part of spatial awareness as well. I've got colleagues at Canberra University who have been doing a lot of work on spatial understanding and mapping and things like that. And they've been using, looking at how getting children to trace maps and follow directions using tracing and things like that, or using gesture, are really important. There's also this research which shows that physically doing or experiencing, so using concrete objects. So, for example, with younger children, we may take them out in the playground and ask them to follow different directions in the playground to learn about your kind of movement and your directionality. Okay, sorry, that was like a quick race through cognitive science approaches. I'm going to move to mathematics education now. Research. Okay. And like I said before, I think it's really important for us to note that these are two different disciplines, but we can think about the connections across them. And so what I'd like you to do while I'm sharing this last part of the presentation is to be thinking about, what do you notice that's the same or different? Okay, because in fact, when I'm looking at this research, I can see lots of similarities across both of the fields, which are helpful to think about informing our teaching. Okay, so your first part here, which comes through very strongly in mathematics education research, is this idea about conceptual teaching. Okay. Okay, so if we're thinking about conceptual teaching, we're thinking about supporting children to make connections, to think about relationships, to think about representation. If we're thinking about procedural emphasis, it's thinking about procedures or rules. Okay. But we can think about an intersection, and this is what I was talking about before. So tasks have an intersection when we're using word problems, multi-step problems, or real-world problems. Okay, and this is a good way of creating this intersection between procedural emphasis and conceptual focused instruction. This study by Yu and Singh drew on data from students and from teachers looking at different teacher approaches. And what they've found is that concept-focused instruction positively affected mathematical achievement. But in contrast, when teachers had procedural emphasis, so strong focus on rote learning or following a procedure, that had a negative effect on mathematical achievement. So they argue also that the teacher support influenced mathematical achievement through students' mathematical self-efficacy and also interest in mathematics courses. So teachers' support of conceptually focused instruction for students supported children's mathematical self-efficacy because children were achieving in those classrooms, but it also led to children being interested in taking mathematics courses into the future. Okay, cognitive activation. So again, this is well grounded, and there's a lot of studies that have been looking at mathematics education about cognitive activation and what the impact of cognitive activation is. Okay, so just to give you an example of what cognitive activation is, and I think that you can probably start seeing here some connections as well to the cognitive kind of science approaches that we're talking about. So this is from a PISA study, just to give you an example of what cognitive activation means. It's presenting pupils with problems in different contexts and asking them to apply what they've already learned to a new context. Giving pupils a problem with no immediately obvious method of solution, or giving them a problem which has multiple solutions possible. Your metacognition part comes through very strongly in this, where we're asking students to reflect on problems, giving them problems that require them to think for an extended time, asking them to use their own procedures for solving a complex problem, creating a learning community where pupils are able to learn from mistakes, and asking students to explain how they solved and why they chose a method. And there's a number of studies which have shown that cognitive activation is one of the most significant impacts on students' learning in mathematics. But interestingly as well, there's also studies that have come out recently, one from Japan by Shimizu, for example, which has shown that cognitive activation is a factor also in reducing mathematics anxiety for students. So that kind of contrasts with this idea that giving children complex or challenging tasks creates maths anxiety. In fact, they've found that doing it in a kind of supportive environment where you're using cognitive activation actually reduces maths anxiety. I'm just watching the time, so I'll just quickly whip through the last ones. Okay, So supporting productive struggle. And there's 3 components of this. So if we're talking about productive struggle, the definition that I draw on is when children or students are delving into understanding mathematical structure of problems and relationships instead of just finding a correct solution. If we're using productive struggle in the classroom in a positive way, we have to think about attribution. So we have to think, what is the struggle attributed to? If students think that it's attributed to themselves, a lack of ability, then often productive struggle will have a negative effect. But if they're attributing it to a problem being challenging or difficult, then it will have a positive effect. So what we can do as teachers then is use motivational talk, talk to children. This is a difficult problem and I know that you can do it. And yes, you might be struggling, but I know that you can learn something from it. The second part of this is metacognition. So we need to be teaching children to actively monitor and regulate their thought processes. Okay, and the last part I think we need to be thinking very carefully about is frustration, because frustration has often been positioned as negative in mathematics classrooms. But in fact, frustration can lead to effort, persistence, and perseverance. And students will be frustrated in contexts outside of maths, and we teach them that that's okay and that they need to get through it. So if you think about sports, if we think about gaming, Lego building, all of those kinds of things, you can watch children become very frustrated in them, but they use it to think about effort and persistence and perseverance. So we can be teaching children that it's okay to be frustrated in the classroom, but we need to get through it with effort, persistence, perseverance. Okay. I'll just quickly go through the last ones. Explicit teaching for peer-based communication and group work skills. Okay, so this is really important, that in fact, we can't just put children in groups and expect them to work together in it to be productive. Instead, we need to teach children how to collaborate, and that must be actively taught. We must think about our grouping practices, the size, composition, the stability, and we must think about interactional support. So how do we teach children to manage tasks and encourage them to take responsibility for their own learning? So this quasi-experimental study by Kutnick down here has showed that, in fact, teaching children relational skills and communication skills, again, supported mathematical achievement. Okay, finally, responsiveness to students' mathematical thinking and learning. So this, again, has had a number of studies which have shown teacher responsiveness to mathematical thinking and learning, particularly acknowledging thinking, eliciting thinking, building upon ideas, and revoicing student thinking all leads to higher mathematical achievement in the classroom. Okay, and finally, using and connecting mathematical representations. So the frequency of mathematical representations, using appropriate mathematical representations, like, this is just a very simplistic example here, but using these problems which incorporate multiple representation, in fact, predict students being able to solve complex problems in the mathematics classrooms. Okay, and I'll just quickly finish off with this kind of final conclusion, which is thinking about how can we bridge cognitive science and mathematics pedagogy. And this really kind of looks at what's the shared, what's shared between them. And I think what we can say is across both of these approaches, it's about cognitive engagement. Okay, so we're needing to be thinking about how do we develop cognitive engagement, how do we deliver information, and the social context of the classroom as all things which impact on children's mathematical learning. Cool.
We may have time for just a couple of quick questions. Anyone? Oh, there's Zoe who's putting up her hand. Yeah.
Oh, thanks. Okay, so hello everybody, and thank Jodie for this very awesome session. So my question is, actually, I was teaching Singaporean math before, and so there are a lot of emphasis on special, like spiral learning. And I was taught if a student cannot master the topic within this year, that is okay because that's spiral learning and carry on to another year. So you don't have to reach a level of mastery just within like one year. However, I have this question for a long time. Is actually about the depths versus the width. So because I think like every teacher probably struggles sometimes to cover all the curriculum topic within just one academic year. But at the same time, Polish students really cannot digest this so much of the content. So what's your idea and what's your thought here regarding should students go for kind of like that first, or students should, just have the width first and Poly way then we Poly revisit topic and deepen topic for another academic year?
Yeah, I mean, I think ideally, and I guess I can only talk in like the perfect world as opposed to what's reality. Yeah, so I mean, I think in fact that if there's a couple of things here, and we're dictated by the curriculum that's set out by the government. So we are placed in this position, particularly now at the moment, of having to teach right across this very broad curriculum. But in fact, I mean, I think your perfect world would be narrow, to actually narrow down and have less in the curriculum and more time to teach those concepts and to teach them in more depth than have this really wide curriculum where we're covering so much, but in, a relatively short amount of time. Yeah. And, how would we manage that? Well, I mean, we could be thinking about teaching particular areas in 1 year and not trying to cover everything every single year. That makes sense. Yeah. And I think, you've got other countries that have good examples of doing that as well, where they're not trying to teach so much, but they're picking and choosing what they teach year to year. Yeah. I mean, I would say that I think we would end up with better outcomes if we had less to teach and could teach it really well than having such a broad range and such a large curriculum to teach.
Thanks.
I don't think there are any more questions. So, Jodie, that was so interesting and very, very useful in our teaching and learning with the new curriculum that's coming out. What you mentioned, both conceptual understanding and procedural fluency both go together alongside the vocabulary and the problem solving. And a big takeaway is that, the explicit teaching doesn't mean just the procedural fluency. You can explicitly teach scaffold conceptual understanding as well. And scaffolding, as you said, is the key with, visual aids and other representations and getting students to understand and keep the practice like spaced practice rather than the master practice. So very, very interesting. Thank you so much for coming online and then sharing your expertise. And there's lots for us to think about.